Chandan, and today I am going to talk about digital signature and the digital signature scheme of Elgamal, its properties, its attacks, and then its derivation and the proving of how that V1 is equal to V2 in the digital signature for Elgamal. So let's get started. So what really is digital signature? It's just a mechanism that validates authenticity and integrity of a message. So now everyone might be wondering what is authenticity and integrity. Authenticity says that whether the message has come from its original source or not, and integrity says about whether the message has been altered or not. So digital signature is a mechanism that validates authenticity and integrity. Suppose if a person A is sending to B some data to B and B is sending to C, then this may not be authentic because it's not coming directly from the original source. But if A is sending directly to C, this proves that the message is authentic. Okay, now let me explain about the general model of the digital signature process, or simply its mechanism. Consider Bob as a sender and Alice as the receiver, and consider a transmission medium or a transmitter in between them. So now Bob wants to put a signature on a message. So how can he do that? He has a message M, and for that M, it becomes an input to the so Bob sends a message M, and that message M will become digital signature. So this message M will become a digital signature algorithm. Now Bob uses his private key and with the help of this private key so Bob takes the message and his private key, and he'll pass it to the generation algorithm, and he'll get a S. S is a set of signatures S1 and S2. It is similar to the Elgamal, in which we will get C1 and C2. So now there is a transmitter in between them. Consider a transmitter nothing like an optical fiber or a medium like through which sender can send it to the receiver. So consider this as a transmission medium. So the message M along with S, it will be sent to Alice. So now Alice receives message and S. So once Alice gets message and S, he uses the sender's public key, that is nothing but YB. So once he uses the public key of the sender, Alice doesn't need to use his private or public key. This mechanism involves only the private and public key of the sender. So now he'll get something like V1 and V2, and he needs to validate the signature. If they both are same, then it means that the signature is authentic and the message is authentic. Okay, now with the general mechanism of the digital signature being done, let me talk about the pros of digital signature. So this digital signature saves a lot of time. So how can it save time? Consider a person who is out of station and he needs to send a signature. So now if the signature has to be sent, it has to be only either through courier or some person medium. But if the signature is digitalized, then it will save a lot of time and there is no need of a intermediate medium like a courier. So that's the first pro or the first advantage of digital signature. And the second thing is cost savings. Since a digital signature doesn't require paper or ink or any printing, it saves a lot of expense. So that's another advantage of digital signature. And the third one is about security. Well, security is all that matters in regard to the digital signature. And how can a digital signature have a good security? So when it comes to security, authenticity and integrity is a priority. So digital signatures make sure and it always reduces the risk of duplication. So if there is a document with the help of digital signature, a document cannot be duplicated or it cannot be altered. So it prevents the original document from being duplicated. That's an advantage. So the first one is environmental factors or benefits. Yes. So since the digital signature doesn't require paperwork, it leads to reducing writing, and which in turn means that it is eco-friendly. Okay, now let me talk about the detailed explanation of the generic model which I have explained earlier. So I'll just explain it individually. Consider Bob sends a message M, and that message will be passed to a hash function. So Bob sends a message M, and that message will be passed to a hash function, and with the help of this we will get H. So once Bob gets H, he uses his private key. So once he uses his private key, he will encrypt it and he will get S, which is nothing but S1 and S2. Similar to the Elgamal. Now this is all about Bob and who is the sender. Now let's talk about the receiver. Alice gets a message M along with the S of the signature. So he has these both, and now he needs to verify whether the signature is authentic or not. There is a cryptographic hash function similar to this. With the help of the cryptographic hash function, the receiver or Alice will get H, and now with the help of the public key, that is YD of the sender, he'll get H dash. So H and H dash is similar to V1 and V2, and now when they both will be compared, if they both are same now, V1 on V2 or H1 and H dash, then it means that the signature is authentic. Otherwise, it is not authentic. So that brings us to the detailed in general explanation of the general model for the digital signature process. Okay, now let's talk about the attacks on the digital signature. The first one is key only attack. During this attack, let's consider C as an attacker and A as the source of digital signature. So during key only attack, C will know only the public key of A. So this is the first attack, and the second attack is in this attack, C, the attacker will know the set of messages and their signatures. And the next attack is the generic change message attack. In this attack, C will change a list of messages before attacking A's algorithm, A's signature algorithm or A's signature schema. And then he will obtain the set of signatures. So here C will not use the public key of A. So that is generic change message attack. And the next one is directed chosen message attack. So this is quite opposite to generic chosen message attack. In this attack, the list of messages need to be signed and they need to be chosen after the attacker knows the public key of A. So here in this attack, the attacker should know the public key of A, unlike generic chosen message attack. But the list of messages need to be signed before the signatures are seen. And the next one is the total break. In total break, the attacker will know the private key of A, or the person who signed the signature. So with this, he can easily manipulate or change the data. So the properties that a digital signature must require are, the first one is it must verify the author name, date and time of the signature. That's the first one. The second one is the digital signature must verify the contents at the time of the signature, not before the time of the signature. And the third one is the digital signature must be verifiable by third parties or certain other applications to resolve disputes. Let me explain about the process of the digital signature. So the first step is the key generation. digital signature requires two steps. One is key generation and another one is key verification. In key generation, four things need to be computed. So let's start with the first one. So consider k as an integer and q as a prime number. So and if GCD of k and q minus 1 is equal to 1, it means that k is relatively prime to q minus 1. Like consider k as 12 and q minus 1 as 16. So they both are relatively consider k as 11 and q minus 1 as 17. Since they both are prime numbers, GCD is always equal to 1. That brings to the end of first step. Second step is computing S1. S1 is nothing but signature. First signature. Alpha. It is equal to alpha power k mod q. Here alpha is primitive root. K is the random integer, q is the prime number. So the third step is k inverse mod q minus 1. And the fourth step is S2, which is the second signature, which is equal to k inverse of m minus S1 into xa. So xa is the private key of the sender, S1 is the signature that is generated previously, m is the message which is generated by the sender, and S2 is the second signature. So now we have S is equal to set of S1 comma S2. Similar to the Elgamal, over where we will get C is equal to C1 comma C2. So this is the first step, and now the second step is key verification. This happens at the receiver side, and he needs to compute V1 and V2. So V1 is equal to alpha power m mod q. Alpha is the primitive root, m is the message, and V2 is ya power s1 into s1 whole power s2 mod q. So this is the public key of the sender. S1 is the signature over here, S2 is the signature over here. And if V1 is equal to V2, then it means that the message has come from the original source. So that is the general process of digital signature in Elgamal. So I have been saying that V1 should be equal to V2 in order for the message to be authentic, or to prove that the message has come from its original source. So let me prove that V1 is equal to V2. V1 is equal to alpha power m mod q, and V2 is equal to ya whole power s1 into s1 whole power s2 mod q, and ya is equal to alpha power xa, or the private key, whole power s1 into S1 is, and S1 is equal to alpha power k, S2 is k inverse m into m minus xa into S1 mod q. So these both will get cancelled, and we are left with alpha power xa into S1 and alpha power m and alpha power minus xa into S1 mod q. So these both will get cancelled, and alpha power m mod q is equal to alpha power m mod q. So this proves that V1 is equal to V2 because alpha power m mod q is equal to alpha power m mod q. To Okay, now let me prove that V1 is equal to V2 in another method. Okay, let's take this to this side. Alpha power m, alpha power xa this one mod q is equal to alpha power. These get cancelled and we are left with m minus xa into s1 mod q. So this is minus because it comes to this side, and since they both have the same base, the powers will get added and it will be negative. So alpha and alpha will get cancelled. We will be left with m minus xa s1 is equal to m minus xa s1. Again, these both are same and it proves that v1 is equal to v2.